Hello class, so this will be CSE 5250 week 2. You may have noticed on Canvas that I've since put up instructions for the first programming assignment, and that is the Sieve of Eratosthenes. Sift the 2's and sift the 3's, the Sieve of Eratosthenes. When the multiples sublime, the numbers that remain are prime. So here are the instructions. I am for the deliverables. I'm asking you for basically the source code. You can use any programming language that you feel comfortable using. And I'm also asking for a screenshot of the program operating, of course. So for those who need assistance with programming the sieve, the first part of this video will be me walking through step by step on how to program the sieve. Just a basic sieve without any fancy optimizations. So you can add optimizations if you would like, if you want to. It's just that whatever the optimizations you put in, they cannot be parallel because we're comparing performance between a non-parallel sieve and a parallel sieve eventually. So no parallel optimizations for now. Just a basic bare bones sieve. And since I'm uploading this to YouTube, I'm going to try my best to add chapters to the video, so you can just scrub through the video to the relevant part, or click on the chapters wherever that interface is, and then you can skip forward to the meat and potatoes of this week's video lecture, which is how did we end up with multi-core CPUs? It's a rather interesting history, but for now, let's look at the Sieve of Eratosthenes. Whoops! Recursion! Right. So the first thing we need to do is we need to make a list of all the numbers, so let's make a maximum number of, say 100. And now we need to make a list of numbers. List of numbers is it's going to have to start from 2 and end at 100. So we're going to have to figure out a way to populate an array with the numbers from 2 to 100. So and because this is Python, there are a lot of conveniences that make it really easy to make super duper powerful programs with just a little bit of code compared to, say, C++. So for our case, we can just use this. Right, so let's do that. List range to max number. And that should give us a array with the numbers from 2 to 100. So this is in Jupyter Notebook, by the way. You can this way I can work on it like a little bit more step by step. So let's just add another cell and do a print operation. So I run everything. There we go. The numbers from 2 to 99. But not quite. We actually need all 100 numbers. So what we need to do is, this is 2 inclusive and max number exclusive. So in order to include the number 100, we need to plus 1. Just a little bit of nuance, because that's basically how this is more or less how a lot of programs loops work. So we've printed out the numbers. Let's add a new cell, and let's begin with, if you've seen last week's walkthrough of the sieve, you'll know that we had to go through you know we had to go through the all the elements in the list for each prime number that we encounter. So it's basically a nested for loop. So for prime in for number in list numbers, prime equals number, or I in range. This list of numbers is not quite 100 elements, so we need to figure out the range of that. So 0 len, that returns the length of an array. List numbers. Go in here. Now, if you recall from that video from last week, we crossed out multiples of a prime number, but they can't be the prime number itself. So we start crossing out numbers. So we start at 2. We have to start crossing out numbers at 4. So how do we know that number is divisible by something else? We use a modular. We use a modulus operation. So if I do integer division, I will get an answer and a remainder. So if I do, for example, 7 mod 5, what is 7 divided by 5? Well, the answer, if I do it in such a way that I get a whole number answer and a remainder, I will get one remainder 2. That tells me that 7 is, well, not divisible by 5. But if I did 7 modulus 7, I will get 1 and a remainder of 0. So this is what we're doing. This is how we are going to know that a number is divisible by something. Oh, and in the case of... And if I did instead, for example, 14 mod 7, I'll get an answer of 2 and a remainder of 0. So that also tells me that 14 is also divisible by 7. There are a handful of divisibility checks that you can use to look at a number at a glance and determine whether it's a number that's divisible by some other numbers. So for even numbers, you can, for example, determine whether a number is even or divisible by 2 by determining whether its last digit is 0, 2, 4, 6, or 8. But that's more useful when we don't have a computer on hand. Since we have to make a program out of this, we're going to use modular arithmetic. So if list numbers I does not equal prime and list numbers I mod prime equals 0. I think this should be a lowercase a. There we go. For our purposes, we're gonna be replacing numbers that are non-prime with a 0. So list numbers I 0. You could, for example, have a second array full of booleans, and every one will be true. You know, let's try that instead. But now I have to figure out how to populate an entire array full of bools. Let's see if this works. Oh yeah, this is more or less how this is more or less how I program things in general. It would be really neat if I somehow knew all the most relevant knowledge that I can ever use, but I just don't. I just look it up I just look it up every time I realize, hey, how do I do this? How do I implement this feature, such and such? Right, so, you know what? Give me a minute. Alright, I think I found out how it's done, so I'm gonna need NumPy for this. Remember that len list numbers returns the length of the array, and we need this to be the same length. We need this list of bools to be the same length as the list of numbers. So one parameter is gonna be how many booleans are we putting, and the second parameter is basically, no, I misspoke. One value is going to be, one value is gonna be how many of the same value we're putting. The second value is the value that we're actually putting. So the type. np.once. Basically, I more or less copied this code. So basically, we should have an accompanying array. That's all true. So if I print that, if I run this and then this again, we should get as the same number of trues as there are numbers in here. Right, so let's do that and replace that with false. I think it's capital F false. And that should be it. This is just one way of writing the Sieve of Eratosthenes. And again, there are different ways of optimizing this. For example, we could have just one array instead of two. That would save up a bit of space in memory if we're doing searches of like 1,000,000 or more. If you do that, we're gonna have to make a few extra considerations on what happens if, when you iterate through this list, you encounter a prime number that was already marked as non-prime. If that makes sense. So what happens if we try this out? At the end, let's add another cell and do print list bools. If I run this cell, it seems to have worked, and if I run this, I have true, true, false, true, false. That should correspond with the numbers 2, 3, 4, 5, and 6. So how do I know that this worked? Well, let's add another cell, and for I in range 0, comma, when list numbers, if list bools I is true, then we print out the corresponding prime number. So we print out list numbers I I forgot the print function. Print. Now, if this works, you should see all the prime numbers being printed. There we go. So this is basically so that's it for the basic bare bones Sieve of Eratosthenes. There are different optimizations that you can use. For example, if you think about it, if you have a highly divisible number, the largest factor it's ever going to have will be half of it. So consider the number 60, which is divisible by a lot of factors. It's divisible by 1, 2, 3, 4, 5, and 6. The largest factor it's going to have, that is it itself, is going to be 30. So for example, you could have this outer for loop here stop halfway through the list, because multiples of all other numbers after that, here's what I mean. If we instead we're looking for prime numbers up to 60, at some point we're gonna stop at 30, because there's no point at we can just stop at 30 because there's no point at looking at any numbers beyond that, because any number beyond that times 2 is just going to be greater than 60. So that's not quite optimal. In fact, an even better optimization is for the outer for loop, you stop at the square root of the maximum number. So that's another optimization you can do, but again, this is pretty basic, pretty bare bones. So that's basically it. If any of you needed help on the Sieve of Eratosthenes, what we're gonna have to do later is find a way to time how long it took for the program to find these prime numbers. In fact, in the instructions, if you look at it on Canvas, there's going to be like optional instructions, or rather recommendations on what else you can put into the program, such as prompting the user how large of a max number to search for, and of course calculating how long it took to find all the prime numbers. So that's going to be it on the Sieve, and now let's look at what's going to be for week 2. Right. Slideshow. So, parallel programming. I may have talked about this last week, but parallel computing is a type of computation in which many calculations or processes are carried out simultaneously. Large problems can often be divided into smaller ones, which can then be solved at the same time. There are many examples of what kind of tasks could be made parallel. In the Section 1 class, we brought up a few examples of parallel program examples. One of them is Bitcoin mining. Another one is rendering a scene in a 3D animation, or just rendering a 3D image into rendering a 3D image. I mean, I've shown an example of that in last week's video as well. So you're gonna have, basically, at some point, you're just gonna have a task that's simply too big for one computer to complete in a reasonable amount of time. There is a question that's related to these gargantuan tasks. And the question is basically, how do you eat an elephant? The answer is one bite at a time. Parallel programming basically asks another question to that question. Who said you had to be the only one eating the elephant? So, depending on the type of workload, you can distribute the work among multiple CPU cores, which is what we'll be doing first, or you can distribute it among multiple computers, which is something we'll be doing on later, with the hopes that it can reduce the time needed to complete the work. So basically, we can get more performance by realizing that multiple CPU cores, multi-core CPUs have been commonplace for a while, and it's in recent times that it started to like skyrocket to astronomical amounts, relatively speaking. Back in the mid 2010s, there have been CPUs that more or less maxed out at 4 cores for ordinary consumers, with higher core counts typically reserved for high-end desktops and servers. And it's only recently that 8 cores has become more and more commonplace. So what we can do is we can write a program in such a way that it can take advantage of those extra CPU cores. So, where did these come from? Where did these multi-core EPUs come from? How are they made? Well, it's made in the same process as any other CPU these days. So modern day CPUs are made by using a process called photolithography. Photo meaning light, lithos meaning stone, and graphos meaning writing. We're basically writing into a stone, a silicon wafer actually. We're writing a pattern into a silicon wafer using light and special chemicals. So, as I said here, this is done by etching a pattern using special chemicals and light into a silicon wafer of a specified size. Now, when this happens, we can make multiple CPUs at once. But one other thing to consider is that this process isn't totally flawless. At the microscale, well, rather at the nanoscale, really, it may be possible to have a few CPU cores, a few chips in here that may have a defect that might render the entire chip unusable. Sometimes it might render it. Sometimes the defect is only minor and it only affects like a few other components, but the EPU itself is otherwise perfectly usable for something else. In this example here, we have a 10 by 10 chip being manufactured in mass on a silicon wafer, and this resulted in almost 250 dies, as they're called. So what's on the silicon? Well, all sorts of things. But mainly, for our purposes, we're looking at the CPU cores and to an extent, the cache. So, a CPU core will have... The thing is, the CPU core can have all sorts of other things, such as this Intel Skylake example. It could also have integrated graphics. So what if we wanted to have more cores on this? Well, all of this is actually a two-dimensional process, because you can't really stack a CPU core on top of a CPU core because you have to shine a light down to the silicon. How do you shine a light onto two different layers? Well, we'll try to circle back to that a little later, but for now, note that this process is two-dimensional, and if you want more CPU cores, you physically have to make the chip, physically larger. In the case of this Skylake processor, you could just get rid of the integrated graphics and just devote that space to more CPU cores. But if you can't do that, then you physically have to add more cores to this chip and make the whole thing physically larger. What does that mean for the silicon? Well, if you're adding more cores, you have larger chips, and if you have larger chips on the wafer, you have a reduced yield. By increasing the size to 12 by 18 millimeters, for example, we have less than half the yield than if we had the 10 millimeter by 10 millimeter example. So, more cores, more silicon, less yield on each wafer. There are other considerations as well, such as, what if we just made these things smaller? And that's exactly what CPU manufacturers have been doing for literally decades. Why? Well, it's simple. Less distance for electricity to travel, less waste heat, and ultimately, more processing power per unit energy. And if we can get the also we can if we can get these dies to be smaller, we can ultimately fit more. We can fit more of these chips on a single wafer, and we can end up getting more CPU dies this way. Much of the 2010s was dominated by CPUs with a node size of 14 nanometers. These days, it's as low as 7 nanometers. And if this trend continues, and currently there are talks about making a CPU with a node size of 5 nanometers and even smaller, as low as 3 nanometers, it's expected that we're gonna see such CPUs in the coming years. But right now, we're at 7 nanometers, and that's pretty small. Oh yeah, these you can also play around with these calculators as well. The past slide here, I used a calculator called die per wafer estimator. There's another calculator that you can play around with, and it's a die yield calculator, and that accounts for defects that may occur on the silicon itself. So you're gonna what you can play around these with these calculators. So for example, you can have this setup where you have nearly 250 dies per wafer, and then you can mess around with the defect density and see how fewer CPU dies that you end up with remaining that aren't defective. So with that, multi-core CPUs have becoming way more common these days because of AMD, which is ironic because this stock image that PowerPoint decided to put up here, that's actually an Intel CPU socket, not an AMD socket. You can look at, there are various videos that online that talk about more about the technical details, but it had to be described in a way that tries to poke fun at AMD. The process is basically gluing smaller chips together. So instead of manufacturing a large monolithic chip for what was then known as the Zen architecture, AMD simply just glued these chips together. Glued in the sense that we now call the beginning of the universe the Big Bang. Big Bang was a term that made fun of the idea of the Big Bang, but now we call it that because right now the Big Bang Theory is, well, a sitcom, but other than that, it's currently the widely accepted theory as to how the universe came into existence. Which is ironic because the name for it was literally poking fun at the idea itself. The history of physics is rather interesting, by the way, but we don't have time. We don't have time right now to go into the really fun and juicy details about the history of physics. Right now, all we have to consider is how AMD managed to increase core counts. Yes, as I said, this proved to be anything but ridiculous. So if you look at the Ryzen lineup initially, a little bit of history. AMD used to be like lagging behind Intel, like by a lot. When Intel was putting out 14 nanometer node CPUs, AMD was stuck on like 32 nanometers for a while. This this all changed when AMD came out with their Zen architecture, which was meant to solve a lot of the issues related to their previous architecture, Bulldozer, or as some people call it, Faildozer. It basically it increased the IPC of their CPUs almost on par with Intel CPUs, but they also did it in a way that it introduced more CPU cores to the end users. So, when the Ryzen 1000 series came out, we had Ryzen 3 CPUs that had 4 cores and 4 threads, all the way to Ryzen 7 CPUs that had 8 cores and 16 threads. This also includes a high-end version of Ryzen called Threadripper that went up to 16 cores and 32 threads. More processing power than the average user may ever need, except for those use cases where we're dealing with a power user and they need to have extra processing power for, say, data science or 3D rendering, for example. We're currently up to the 5000 series, which is more or less the same as the 3000 series, but this is what the 3000 series lineup looked like at the time. The biggest change is the maximum core counts, of course. This is the first time we've ever been introduced to the Ryzen 9, which maxed out at 16 cores per CPU. Look at I think it's AMD's CES, I think it's called. When Lisa Su, CEO of AMD, teased the Ryzen 3000 series, she famously held up a delidded AMD CPU that... Let me just find a picture, hold on. So, as I said, during the first quarter of 2017, which is like January and such, Lisa Su made a presentation on Ryzen 3000 and famously held up a CPU that basically looked like this. Remember when I said that the CPU die has all sorts of stuff on it, such as cache and memory controllers and CPU cores? AMD bucked that trend by modularizing the entire CPU. So here, this smaller module is actually where all the CPU cores live. This larger module is basically everything else. And what's devious about this chip is there's suspiciously enough room to have a second module here. And that's basically what happened when we had the Ryzen 9s come out. 12 cores and up to 16 cores. So, basically, these smaller modules had 8 CPU cores. By having an extra module on the same package, you would end up with 16 cores, and that's how we end up with these high core count CPUs. And at this rate, it's just gonna become more and more commonplace to have these high core count CPUs. So, us, as programmers, have to account for the fact that now we have to program on these things, and we have to figure out how. So let's get back to the presentation. So, more cores, more performance, right? Well, not quite. When we write programs, we have this idea, this expectation, that instructions are executed sequentially. Does it make any sense to execute instructions in any other order? Well, sometimes it does make sense. If you have, for example, and I'll just type it out in here, you have a situation where you have int a equals 355 int b equals 113 and int float a equals 3.1416. If you had a situation where you had variables like that being initialized one at a time, it is possible to have them all execute at the same time. This is because the initialization of int a does not affect the initialization of int b. However, if you had something else like this, then basically we cannot have this happen before int a and b. If I do that, the compiler will basically say not defined. That's not going to work. So if you have a situation where you have little blocks of code, or even just lines of code, that can be executed in any order, that is an opportunity for parallelization, where you can have all those lines of code being executed at the same time. I work with another professor who likened programming as following the steps in a recipe. So consider this example of a lasagna recipe that I actually cooked the other day. Does it make sense to mix up these steps? Well, in a weird way, it kind of does if you look at steps 1 and 2. Step 1 is basically cooking ground beef and onions and garlic and tomato sauce together until it's all nice and heated up and thoroughly cooked. Step 2 is mixing up the cheese mixture, so mozzarella, cottage cheese, and parmesan, together in a large bowl. So, in this example, it is possible to just mix all the cheese and then make the meat sauce, or make the meat sauce first and then the cheese. However, it does not make sense to do step 3 before steps 1 and 2. Spoon a layer of the meat mixture. What meat mixture? So yeah, it doesn't make sense to do step 3 before steps 1 and 2. So it may make sense to do step 1 after step 2. So this requires a bit of thinking. It is possible to do step 2 at the same time as step 1. Here's how. You cook the ground beef until it's nice and brown. You add the onion and the garlic. And then you cook that down until the onions are nicely cooked. And then you add the tomato sauce, the tomato paste, and everything else. And stir well until it's combined and heated through. You can just stir, leave it on the burner at low heat, while at the same time you mix up the mozzarella cheese, the mozzarella, cottage cheese, and parmesan in a separate bowl, all while the meat sauce is cooking. So that's basically parallel programming right there, or rather recognizing where tasks can be done in parallel. If you're in a situation where you're making lasagna on a super duper tight time schedule, this kind of work will literally shave significant amount of time if you're repeating this recipe like a few times a day. But as Adam Ragusa famously said, that kind of work does not really translate well to home cooking, because what's gonna be the biggest time sink in this recipe? This is actually a slow cooker recipe. The largest time sink is when you cover and cook the lasagna for 4 to 6 hours. So really, doing step 2 at the same time as step 1, it may save some time, but compared to if you just did the 2 steps sequentially, the time savings might not be all that much. This relates to something called Amdahl's law, which we'll also get to later on when we look at how the Sieve and its parallel versions performed. So, with that in mind, do we just have to, when we as programmers look at code, do we have to manually write code based on whether we can determine whether this is a task that can be made parallel? Or is this something that we can offload to the compiler? Basically what I'm saying, is there a way we can automate the writing of parallel code by placing, by giving the, is there a way to make a compiler or configure a compiler such that if it's given a program, it can generate a parallel version of that program? Also, is there a limit? How much performance can we get out of parallel programming? Or rather, how many cores is too much cores? So those are just a few questions to keep in mind when we start actually making a parallel sieve. Here's the sources, and what I'm gonna try to do is, if I find any interesting videos worth watching, I'll link them at the end of the presentation. So I posited the question: is there a limit? Is there a point where too much cores is too much? Some of these videos are basically review on how CPUs are made, and that isn't getting into other things such as pipelining and clock speed, and how IPC became the de facto measurement for measuring performance of a CPU. Because at one point, clock speed was all you ever needed, and then pipelining became a thing, and it kind of screwed up how we measure performance of a CPU. This is why, if you took one of AMD's bulldozer CPUs, someone famously overclocked one of those to 8 gigahertz, and somehow does that kind of performance hold a candle to Intel's modern day CPUs? It's not so much an apples to apples comparison anymore, because literally the architecture changed, but basically the architectural differences is also greater when you consider when they're made. So yeah, these are videos I would recommend that I these are recommended videos that relate to what we've just talked about today. And that should be it for week 2. I may have a follow-up video on what to do with OpenMP either later this week or at the beginning of week 3. So that should be it. Thank you, class. I'll see you in the next video.